Thank you, Kaden. Let me start by thanking the organizers for the invitation. It's such a great pleasure to be here in person in KITP. Yes, so please, during the talk, interrupt me in the middle of the talk if you have questions. That's perfect. What I want to tell you today is about a story of simulating dynamical physics of BCS superconductors in systems with long-range interactions. Most of the, or part of the work that I'm going to talk about is actually not published, so it would be, I'm bringing it here to get your feedback. That would be great. All right, so let me start just by start with equilibrium phase transition. That, of course, is a topic that all of us know here, but they are characterized by an abrupt or non-analytic change in the free energy of many-body systems as a result of slow changes in systems parameters. It can be the temperature for the case of a classical phase transition, or it can be other control parameter, for example, for quantum phase transition at zero temperature. The important part that I want to bring is that these are typically described by another parameter, which is the quantity that changes non-analytically abruptly at the critical point. So what I'm going to talk today about is a similar but very different still a class of transitions that are non-equilibrium phase transitions. They have a similar but also very different points with respect to the equilibrium ones. Well, I want to emphasize that the topic of non-equilibrium phase transition is really broad. And for this talk, I'm going to exclude the ones that happen in open quantum systems. So I'm going to restrict to the ones that have that happens in closed systems and therefore conserve energy and involve unitary dynamics. Also, there are various definitions of non-equilibrium phase transitions. What I'm going to focus today is the one that share the similarity to the equilibrium ones, that is a long time or an average order parameter, that is the quantity that also features the non-analytic behavior and distinguishes two distinct dynamical behaviors in the system. There is an order parameter, and that's why it's similar to the equilibrium ones, but in contrast to these ones, they are not found by minimization of free energy, and moreover, they open or they have no symmetries. And moreover, they allow for the robust generation of useful entanglement states that can be very exciting. I want also to emphasize that there are other type of phase transitions, dynamical phase transitions, that are characterized by a non-analyticity on the Lord mid-echo, and I'm not going to include them in this discussion, but there is a very nice review by Marcus Heil if you want to look at them. All right, so the point is that even though there has been a lot of interest in theoretically and a lot of investigations in dynamical phase transitions, it's only recently that experiments have been able to reach the conditions in order to actually observe them. So, for example, one of the first experiments happened in 2018 using arrays of trapped ions that have power law interactions, and they were done with arrays of 53 ions that they show even beyond in-field behavior. But lately, after that, there has been other type of observations that were targeted instead to several thousand to million particles. And these were, for example, using fermionic atoms, using the control parameter, the scattering length, that can be controlled by a Feshbach resonance, in potassium atoms trapped in a dipole trap. These were observed in the Toronto group and Joseph Twalwesen. Also, we have observed another type of dynamical phase transitions in a cavity at Gila. There has been other phase transition observed, for example, using sidebands in a thermal gas of rubidium atoms in Hanover, other in Lumin Duan's group in China, where they also use a BEC, but they use spin changing collisions. So, and maybe there has been others that I'm not citing here, so I'm not being completely, this is just a few of them. And also, as we heard from Ben's talk yesterday, there is another broader class of systems that have seen experimentally dynamical phase transitions where dissipation has been key. But in this case, I'm going to focus in Kavli QED systems first, and especially we are going to focus in systems at Unitarity. All right, and the target that we have is trying to simulate phase transitions, dynamical phase transitions in BCS superconductors. So with that target in mind, let me start by introducing this simplified or reduced BCS Hamiltonian. In this case, is the S wave character, where we have two different types of spins, fermions with the spin up and down. And we have two terms that describe the dynamics or govern the dominant type of the dynamics. This Hamiltonian is written in momentum space. We have the dispersion relation that is associated with the kinetic energy and the measure respect to the chemical potential mu. C is the creation, or the C dagger, the creation operator for fermion, of a fermion with momentum K as spin sigma. And this other term that describes the attractive S-wave interactions that favor the formation of Cooper pairs. So here you see that the Cooper pairs are formed between fermions with different momentum and different speeds. Now, one of the simplifications that we can make is that if we are working at very low temperatures, then the Hilbert space that describes the dominant physics only consists of Cooper pairs and empty sites, because the states with a single fermion are energetically costly. So the Hilbert space is reduced to these two states, and therefore we can map the system to what is called Anderson pseudo-spins, where a spin up corresponds to a Cooper pair and a spin down to a backhand site. So with this picture, then this Hamiltonian can be written in terms of spin creation and annihilation operators. So in this case, the operator that destroyed a Cooper pairs is equivalent to flipping a spin from up to down. And we can count the number of the difference between spins, the spins up and down. So we can define an effective SC operator that we can use to replace the kinetic energy. So in this case, you can see the Hamiltonian is simplified to the one of a simple spin model. Is written in momentum space, where the kinetic energy is associated with a transverse field that is inhomogeneous, and the interaction term maps into a collective and all-to-all S plus S minus, where S plus is the collective spin operator, is summing over all possible spins. So, okay, the other interesting part is that Hamiltonian is integrable. It belongs to the type of Richardson go-down model, and there has been subject to a lot of investigation in condensed matter. Of course, the ground state is very well understood, but there has been different investigations of what happens when we dynamically prepare these phases. So the order parameter, that is the gap function, in this case, in terms of the spin, is associated with the expectation value of S minus operator, that for the spins is associated with the spin coherences of the system. And the idea here is that what about if we quench this gap parameter suddenly from one value to the other, and we can see what are the different phases that appear in the system. And actually investigations then reveal that there are three distinct dynamical phases that characterize the non-equilibrium dynamics. There is one phase where you simply quench the parameter to a small value, and therefore the order parameter disappears very quickly as a function of time. This is called phase one. In the case of phase two, on the contrary, there is an order parameter that oscillates with transient oscillations, but then at long times, actually it reaches a finite steady state value. And then there is the phase three, where the order parameter continuously oscillates. The amplitude of the order parameter continuously oscillates as a function of time. This was connected with the time crystal phase thought initially by Wilczek. So, but the important point is that all these phases are very well studied and characterized, because this model, as I said, is integrable, admits an exact solution, and there is some technique that is called lax construction, that you construct a polynomial whose roots actually characterize the frequency spectrum that rule out the dynamics. Well, theoretically, there has been studied. However, experimentally, to see them, it has been very hard. I mean, there are many papers that have been trying to actually predict and understand the different phases, especially in the context of ultra-cold atoms. there has been efforts in condensed matter system in actually thin field superconductors with the advantage of terahertz pulses, trying to understand evidence of this phase 2, for example. And even though there are some evidence, it has been hard because, I mean, you need still ultrafast pulses and the quenches are kind of small. So the advantage would be if we can see these phases in cold atoms, and it has been hard in actual pair fermions because the temperature is very cold. So we have had some proposals. I mean, this is the experiment that we did in collaboration with the group of Joseph Taiwansen, trying to see phase 1 and phase 2. I'm not going to focus about this experiment in this talk, but I'm going to try to talk about possible experimental observation in cavity QED systems where we expect that we can see all the 3 phases. Okay, and this has been inspired by work in collaboration with James Thompson group at JIRA. So the basic idea or the motivation is that we can have strontium atoms in a cavity, and strontium atoms, that are the atoms that form, are the basis of the atomic clocks, the state-of-the-art atomic clocks, have a very long-lived transition that allows us to use the ground and the electronic states that are directly connected by the cavity as our effective pseudospins, spin 1/2 system. So sometimes we're going to use the 3p0, sometimes going to be the 3p1. I mean, the important part is both of these states are very long-lived. One extremely long-lived that has a line width of millihertz, so 100 seconds coherence time, a lifetime, and the other has a line width still narrow, 7.5 kilohertz, that gives us 22 microseconds lifetime. So they're much long-lived than typical alkali atoms. So we can work on them during the experiment in real time. So the dynamics that describe the physics of these atoms when they are placed in the lattice is called Tavis-Cumming Hamiltonian, where here instead of we are going to focus in the case of a standing wave cavity that admits a single cavity mode, and this cavity mode is characterized by this creation or destruction operator A. So we have the Hamiltonian is A daga A, where delta C is the tuning between the atomic transition to the cavity resonance, this delta C. G is the single particle Rabi frequency, and that term represents the atom light interaction that destroyed a photon and create a spin excitation. S plus again is the collective spin of the system. So in this case, you can see that the interactions are really, I mean, it's coupled to all the spins. And what the key part is that we are going to focus in the regime where the cavity detuning is much larger than kappa, the cavity decay, and this square root of Ng. N is the number of atoms, and still much larger than the spontaneous emission. In this regime, the photons, the photons in the system are only virtual. They can't be adiabatic eliminating because they cost so much energy to create the photons. And therefore, in this case, we can basically slave the photons to the spin. So when we adiabatic eliminate, you can see that the field operator becomes proportional or follows the collective spin of the system. And you can see that if I do that and replace this in the Hamiltonian, the net effect is that I have an interaction that is of the form S plus S minus, that physically it means that in my system, when I have one atom in the excited state, it can emit a photon, and because the cavity decay is very slow, then the first process is that this atom is virtually absorbed, this photon is virtually absorbed by another atom, and the atoms start to see flip-flop, to experience flip-flops, similar to what happens in polar molecules, Rydberg atoms, even trap ions, other cavity systems. The important part here is that the interactions are fully collective because are mediated by the photons, and therefore infinite range interactions. This parameter chi is proportional to well, basically the tuning divided by the kappa. And the important part that I want to bring up is that even though there could be super radiant emissions, that is all the particles decay to the ground state stimulated by the collective effects, this process, the ratio between chi and this gamma is proportional to the ratio between delta and kappa, and this we can make it much more larger than 1. That means we can neglect any superradiance event in these systems, and the dynamics is mainly unitary. This Hamiltonian, just trying to understand how the behavior of this Hamiltonian can be rewritten as s squared minus sc squared. The first term is what it provides some gap protection and is connected to the phase 2 that I talked about before, that stabilize a coherence in the system, that stabilize the superconducting order parameter. And this other parameter, sc squared, the other term, the Hamiltonian, is kind of a collective precession. Is called one-axis twisting Hamiltonian, that in principle is useful to generate the spin squeezing. But for this talk, I want to focus on in this gap protection, this part of the Hamiltonian s squared. If we are in the collective manifold, then this is just a constant and nothing happens. Basically, s plus s minus behave identically to sc squared because this term is a constant of motion, but I'm preparing everything in the collective manifold. But on the other hand, if I have some dephasing or something that is inhomogeneous, like what is going to be the kinetic energy of my system, what is going to emulate the kinetic energy, you can see that in this Hamiltonian doesn't commute with total S, this environment of this noise. It doesn't commute with total S. So if I have this Hamiltonian by itself only, what happens is that if I prepare all my atoms initially in the collective manifold, the system is going to decohere very quickly and go to the S equal to 0 sector. And this is what emulates phase 1, when I don't have any coherence and the system decays very quickly. So this is kind of the emergence of phase 1. On the other hand, if I have a large chi, so when I have when I'm protected my system, when there appear these terms, appears in the dynamics, it opens a gap between s equal to n½ and s equal to n½ minus 1, and therefore it's energetically costly for the noise to actually transfer atoms from this to decay, to flip a spin. I mean, the system going to be mostly ferromagnetic. All the spins wants to keep aligned, and this is what stabilizes the phase 2 in the superconductor. So just mention that experimentally, we have been able to measure this gap in James Thompson's group, and the idea was very simple. The idea was maybe we can introduce some dephasing, let the system evolve, and then rephase the system by changing.
Can I ask a question?
Of course,
so that
please.
argument, does that work for white noise, or do you need
this is not white noise. This is the Hamiltonian is a static noise for the moment, and this is going to resemble the kinetic energy of the fermions that are completely static. But it's completely right that if it's white noise, I don't have any gap protection because the frequency span I mean, is a white noise is very broad in frequency space, so the gap protection doesn't work. Yes, the noise is just somebody, when we apply here, the noise is just some dephasing that we appear via star shifts, some static star shifts that can change because the harmonic potential can be quadratic. It changes from one atom to the other, and this can be applied in the experiment easily. So that's the idea. So he turns on an AC star shift that changes significantly from one atom to the other, then let the system evolve for some time, and he can control the detuning of the star shifts such that after he can completely reverse the sign from positive to negative and rephase the system. So you can see that in this case, if we have only a sc squared Hamiltonian, then nothing happens because these terms commute with the sc squared Hamiltonian, and therefore it's like I don't do the dephasing protocol. On the other hand, when I have this chi sc squared, these two don't commute, and what happens if even I prepare my atoms, for example, imagine that I prepare them very close to the south pole, all collective, and I dephase the system, then very quickly they're going to go to the minimum value of total S allowed by the projection. So, for example, this is going to go, if I have component here in n², this projection that is minus n½ plus 1 is going to go to the only allowed, that is a total S n½ minus 1. And if I have S equal to minus n½ plus 2, it's going to decohere to the minimum allowed, conserving SC, because SC is conserved, total SC is conserved. So at the first part, I'm going to reduce my S as much as I can. But notice that during the holding time, because the different S sectors have different value of energy, so there is an energy difference between S equal to n-half and S equal to n-half minus 1 proportional to chi n. There is an energy difference between S equal to n-half and S equal to n-half minus 2. S equal to n-half minus 1 and S equal n-half minus 2 proportional also to chi n. So there is going to be a different phase that I acquire depending of the total S that I have. So this is one phase that accumulates. In the Hamiltonian, and when I rephase, then I'm going to come back exactly with to the maximum S equal to n-half after the time reversal, but I did accumulate some phase during the holding time. Due to the SC square Hamiltonian, I also going to accumulate a phase depending of the total S that I have in this case, because the total S is not, SC is not affected by the dephasing. I just acquired the typical energy difference between different projections along the SC direction. The important part you can see is that this phase from S square and the phase from SC square is exactly the same. So this phase cancels out when I have the two terms in the Hamiltonian. So as a result of this protocol, I don't have any phase accumulated. On the other hand, if I don't do any of the dephasing, I just get the term that is proportional to SC square, and I just get this phase. So in one case, I do have, when I do not do the dephasing, I get a phase proportional to, proportional in this case to chi n, and in the other case, I don't get that. So as a result, I do measure the energy gap, and you can see that this was measured in the experiment. This is just telling you that we can measure this energy gap. It's there, and this is existing cavity QED system, and we have seen it. So, but now let's try to see how is we want to prepare the different phases in emulate the phases of superconductors. So the basic idea is just I want to go from momentum space to position space, and then I can engineer, if I want to engineer the two different terms that emulate the fermionic system. So the first term, as I show you, naturally appear because of the photon-mediated interactions. Now, these two terms, the kinetic energy term, the only thing that I need to engineer is the presence of a Fermi C. I mean, we know that, for example, in the BCS superconductors, the ground state is going to be full, or each momentum state that is low energy is going to be filled by two particles. And then after some Fermi energy, everything is going to be empty. Remember, Cooper pairs are up, the empty sides are down. So what characterizes is that you can see that whenever the energy is measured with respect to the chemical potential, so there is a correlation between magnetization, that is, and the sign of the energy. If the energy is positive, the spins are pointing up. If the energy is negative, the spins are pointing down. So this is the type of kinetic energy that I have to engineer in my cavity system in order to emulate the Fermi C. And the proposal is trying to use either some magnetic field gradient that is going to change the orientation of the spin, and half of the spins are up and half of the spins are down. But more easily, the proposal that we have is use two internal states of a strontium atom. So, for example, two different nuclear spins, a spin minus 9/2 and a spin 9/2. And this is the idea. If I start with all the spins and then I rotate them both to the x direction, and I apply a magnetic, because of this, the energy difference between up and down, then one starts to rotate in opposite directions depending of the spin. So if they are in this 9/2, they're going to rotate along one direction, and if the other spins are minus 9/2, they're going to rotate in the opposite direction. So they start here and they're going to rotate at opposite direction in the xy plane, and you can see that this gives us what we want. One of the spins are pointing along that the ones that have minus energy, epsilon energy are going to rotate in one direction. The others are going to rotate in the other direction, and therefore I engineer kind of a correlation now in the xy plane between the two spins, the two different spins. And then I also have something that is a dispersion I can introduce same random star shifts to add some, so the dispersion relation is not completely uniform, but just create the kinetic energy. So with these two ingredients, we have computed what are the different phase diagrams, as a function of the opening angle delta phi. And we can see that depending on the opening angle delta phi, that can go from minus pi to pi, and the disorder that we implement, we can implement phase 3, phase 2, or phase 1. Basically, in phase 3, when epsilon 0 is larger than the disorder and is still dominated by interactions, we can see the oscillations of the order parameter. In the second case, phase 2, when actually the epsilon 0 is small compared to the disorder of the system, but still much smaller than the interaction energy, I have an order parameter that saturates as a function of time. And in the other case, where the disorder dominates, I just decay, emulating the different phases. The detection of the cavity is very easy because the field going out of the cavity has information about the phase. And actually also the magnitude of the field going out, it gives me also the information of the amplitude of the order parameter. So basically, this is a numerical calculations with the parameters in the experiment. We can see that we can, for example, go, in this case, at phi equal to pi, we can go from phase 3 to phase 1, and we can see for phase 3, we have positive and negative energy because of the oscillations. Or if we are going to have a cut, for example, from phase, we are going to go from phase 2 to phase 3, along this vertical direction, we have something that saturates or something that oscillates as a function of time. Okay. Now let me go to the next step. I mean, S-wave superconductors. Maybe I'm going to take 3 more minutes, so 6. So the basic idea is that S-wave superconductors are interesting, but the most interesting superconductors actually are P plus IP superconductors, because they admit not only superfluidity, but also topology. So we can have Cooper pairing of electrons with carry angular momentum. We can have gapless chiral edge states that circulate around the boundary, analogous to the quantum Hall state. In this case, a carry energy instead of charge. And moreover, they have admit what is called Majorana zero modes. Emulating these P-wave physics in collatons, however, has been very hard because of the centrifugal barrier. P-wave interactions are very weak, and we have tried to enhance them via fetchback resonance, but they're lossy, so typically it doesn't work. So one of the ideas, we can use trap ions to actually simulate these dynamical phases. So very quickly, the Hamiltonian of topological P plus IP superfluids. Now they are spin polarized, and it's very similar to the one that I showed before, no spin, but now here the pseudo potential is Q time dot K. This is in momentum space. Everything is very similar. We can also do a pseudo spin mapping. And here the trick that sometimes we do is that even though this doesn't break time reversal, but sometimes we can write the Hamiltonian instead of this as the superposition of the minus and the plus contribution. We can break time reversal and only choose one of these contributions and write the Hamiltonian in this form. So this is a time reversal symmetry broken model, but this also admits a solution in terms of the Richardson-Goldau model. And there has been a lot of work trying to understand the dynamical phases. They're similar than before, phase 1, phase 2, and phase 3. But the important part here is that when you have phase 2, you can have two distinct, topologically distinct phases, the BCS that is topologically non-trivial, that has a texture of the spins, and that have a non-zero winding number that can be characterized by the difference between the central spin compared to the spins in the outside, I mean, in the edges that are all pointing down because it's vacuum. Or the BEC that is actually topological trivial and have all this, the direction of the spin at the center is the same that the spins outside. And well, so the idea that we have to, I mean, similar phases, again, phase 1, phase 2, and phase 3, similar properties, except that you can distinguish phase 2 between winding number 1 or 0, because there are two different types of topological character. So the idea here is trying to use arrays of ions that self-ensemble themselves in a penning trap. They form two-dimensional arrays of planar crystals. These are trapped in a penning trap The idea here is the trapping is done by applying a strong magnetic field and make the ions rotate such that the Lorentz force generate a radial confinement. And in this case, we can encode two spins in the lowest hyperfine levels of the beryllium ions that are split by hundreds of gigahertz because they have a strong magnetic field. But the idea here, and I mean, maybe I'm running out of time, but the idea here is that we apply Raman beams to actually generate forces on the spins that depend on the internal level. So basically, we can introduce two pairs of Raman beams that are detuned by some frequency mu, and we can generate some what is called a spin-dependent force that couples the position of the ions, depending on the orientation of the difference of the Raman beams, with the position with the spin. Here, SC is the spin of a given ion, and we can also apply a microwave that introduces a collective rotation. Because the ions are formed as self-assembled crystal, what happens is that the position of the ions is not independent, but is determined by the actually drumhead modes of the crystal. This along the C direction. So I have to expand this C operator in terms of these normal modes of the crystal. And moreover, along the X direction, the ions are rotating. I mean, the ions you look at how the ions are doing in the lab frame, they're rotating. So there is a position that is Ri cos omega RT times the phi's azimuthal angle. And then also I have the microwave. So here, I mean, I'm running out of time, but the idea is that I can set the mu, the bit node, such that I go to the rotating frame. Then I can select only a certain terms in the Hamiltonian that has a form S plus I, but here this phi I comes from the rotation of the spin. So I can select from all these terms that I have, only this term, this is slowly oscillating. And you can see here the R is coming from the radial coordinate of the ions. And if I set this detuning such that it's still larger compared to any other energy scale of the system, I can also adiabatically eliminate the phonons. And then the leading Hamiltonian that I get is very similar to the one that I need, but instead of momentum space, in position space. And moreover, I can apply a Raman beam, and I can use the beam waves to actually also control this term that depends on the position of the ions. So basically, with these two tools, I engineer exactly the P plus IP Hamiltonian that I wanted to have in the fermionic system with full degree of control. So with that, I mean, we can also prepare, select some terms in my Hamiltonian to actually prepare a state artificially, just that, I mean, by selecting some, by preparing some, choosing some mu, I can also select in my Hamiltonian a rotation that actually prepares a non-trivial order parameter, because of course I have to select something that is non-trivial, that have the spin texture at time equal to 0 in order to let the system evolve if I want to have non-trivial phases. So I can also set some parameters in my bit node, so I can create an initial state that has non-zero topological order parameter. And with that, our simulations indicate that not only I can simulate the different phases, phase 1, phase 2, phase 3, but because we have only 200 ions, beyond field effects also start to play a role. So this is, I'm going fast here. This is as the different order parameter as a function of time. And I see a mean field solution, and we have simulations that can include the quantum noise of the system. And we can see that, well, even though there is some initial behavior that will allow us to distinguish the different phases. So this phase 1 decaying very quickly, phase 2 asymptotically stabilizing to one value, phase 3 oscillating, but oscillation decaying because of quantum fluctuation. Still, I can see reminiscent of the phases in the system as a function of time. This is one. And finally, we can distinguish the different non-trivial topology of the two different phases, the BC, for example, and the BCS, because they are going to have spin textures that have an order parameter that is rotating along the different direction. So in one case, the order parameter is rotating counterclockwise, in the other is clockwise, and depending of the rotation of the order parameter that I should be able to measure with the ions, I can distinguish if the topological non-trivial phase, that is the BC phase, or the topological non-trivial phase, just by measuring the orientation of the rotation of my order parameter. So with that, we hope that we should be able for the first time to see P plus IPY physics in a system. It's not fermions, but still it has all the different phases that are predicted to exist in P-wave superconductors. With that, I think I'm running out of time, but hope I can tell you, I can convey you that we have systems that I can actually be simulators of the non-trivial BCS phases in superconductors. That, there is moreover with the possibility not only to see the predicted mean field phases, but to see in additional the beyond mean field corrections. And well, in the future, we should be able to not only see these phases, but go to from 1 to 2 channel models by having the photon or the phonons alive, and moreover generalize it to larger number of internal levels. And with that, just let me thank the experimental collaborators on my theory group, and thank you for your attention.
Online, feel free to just raise your hand. Or I see will be next.
So I assume that you have to measure the spin texture. So you're mapping momentum space to position.
Yes.
So to see this observable, you will have to
yes.
Basically do a single site resolution.
Not necessarily.
There is a collective.
No, there is a collective. I was not. I could. So by choosing the bit node nu equal to omega r, we can prepare this type of Hamiltonian. So from all these terms that are in this optical dipole force, we can generate a Hamiltonian that mimics a rotation but in a way that each spin has some, you can see that the phase depends on the azimuthal angle of the spins, and the position, and the amplitude depends on where it's located in the crystal. So you can see that if we apply this drive, and I do a short time expansion, maybe it's not that obvious, but if I apply this drive and I do a short time expansion, the total behavior of expectation value of SC, that is the magnetization that I can measure by fluorescence, actually has information of this order parameter. I will have to show you the math, how you see, but basically the idea is that you apply this drive that has the character of the order parameter that you see.
So it's intuitively, basically you are rephasing all the spins because the tuning is exactly the...
It's exactly the texture that I want to see. So exactly the drive really has the texture that I expect from the order parameter. So by applying this, so after the measurement, for example, I stop the interactions. I stop the interaction and just apply this for a short amount of time. And then I measure the expectation value of SC, kind of a type of Ramsey protocol. Then I can see what is the order parameter by measure fluorescence.
I see. Okay, thanks.
Great. Tarun, do you want to ask your question next?
Sure. Thank you. I had just one question about, so which of these features, right, you have these three phases or regimes, which of these survive if you make the model, let's say, a power law interacting rather than all-to-all couple, or let's say short range? How much of the fact that you have the special model which all-to-all interaction without any decay of interactions?
Yes. So in the case of trap ions, in principle, we can have power law interactions naturally, depending of the bit node. But what we are going to do here, let me ask you if the question is, you want to understand how susceptible or how all-to-all I have to implement the interaction in order to see the phases. Is that the question?
Yeah, just a theory question, whether if I have is there a short range model which has similar physics?
Okay, this is in momentum space. So notice that, the actual interactions in principle in position space are short range, but because we are transforming to momentum space, they are all to all. So what we are trying to do is try to use these long range systems that actually even in a space have all to all interactions to emulate the momentum, space in short range systems. Yes, so I mean, this Hamiltonian that I write for the superconductor is the real Hamiltonian that describe BCS superconductors, even when they have just relatively short range interactions.
Oh, sorry. Okay.
Column interactions.
I see. Okay. Okay.
So, but we are taking advantage that we have systems that actually emulate these very long range interactions, and we are mapping what is used to be momentum in the superconductor to a real space in our simulator.
Mm-hmm. But if you make the model non-integrable, even then these three phases exist. Suppose you.
I think so. I mean, they are quite. I mean, there has been a investigation of how much. I mean, even though you break the integrability, because of course these Hamiltonians, when you have pure all-to-all interactions, they're integrable. Even you break a little bit integrability, maybe you still see the phases at intermediate times. Maybe at very long times, everything is going to be thermalized. But maybe at intermediate times, as long as you don't, I mean, as even relative long-range interactions, but not all-to-all, it still can give you the behavior. So I can tell you that the experiment that we did with Joseph Tygwasen was using actually fermions that have S-wave collisions, but in momentum space, they look again all-to-all, and we were able to see these phases too. So.
I see. Okay.
Can I quickly comment on that, or should David Wise speak first? I'm asking the chair.
I couldn't hear that, so.
We didn't hear that.
Jameer, why don't you, if you have something quick, go ahead and chime in.
Yeah, just quickly for Tyrone. So think about Ising model with long-range interactions, right? There is a values of alpha between 0 and a critical one given by dimensionality, where the effective model is the LMG, the fully connected.
Indeed, yes, yes.
So we have explored that with some collaborators. I can send you the paper. And the answer is that in that case, although strictly speaking not integrable, you're going to see the same DPTs. Then you enter in the true long-range regime, where still there have been studies, and as Ana Maria pointed out, you see along times the phases in a sort of trithermal fashion. And finally, when you become truly short range, typically because you have finite energy density, order can be destroyed and will die quickly. This is work by Misha Knapp and Alessandro Silva, and then we had a number of works on time-dependent spin wave theory that supports this. I will send them to you.
Yeah, thank you. Makes sense. Yeah.
Dave, why don't you ask your question next?
So, Anna, is it possible to have the hint of any of these dynamics in condensed matter systems?
Yes, so there has been in thin field superconductors, they have been experiments that apply a terahertz pulse. So it's not so strong that it destroys completely the superconductor. It's still moderate because the energy is proportional to the gap. And there has been indications of the transient oscillations that you expect for phase 2. So in phase 2, the order parameter has transient oscillations actually, and the oscillations is at a frequency twice delta, twice the order parameter. And there has been some indication in condensed matter systems that in superconductors that this is associated with phase 2. And Matt Foster, who has done all this theory work also in connection with colatoms, he has been trying to model these experiments and have seen, I mean, evidence that maybe indications that is associated with these dynamical phases. But there is a lot of debates of to what extent you are really not doing pair breaking of the Cooper pairs when you apply the poles. I mean, there are a lot of debates associated with the actual observation of this oscillation of the order parameter. So.
Is that what they were looking for when they did those experiments?
They were trying, yes, they were trying to look, let me look at these phases. That's what they were trying to see oscillation. Sorry, Hopefully you can see now my screen for phase 2. They were trying to see the oscillation, the transients of this. You see that at short times, when you see that there is some oscillation of the order parameter, this transient oscillation, this happens at twice the gap that you reach at very long time. And they were doing palm probe experiments that were revealing some type of these oscillations. Well, I'm not expert on that, but Matt Foster has tried to use exactly this lax formulation, trying to model, including other terms in the Hamiltonian associated with the pump, and seems that he can reproduce what they are seeing during the dynamics.
Okay, thanks.
Totally, if it's quick.
Okay, yeah, I have a quick question. So if you have sort of non-integrable model, then eventually things will normalize. So time averaging will give you like equilibrium. I'm just curious, and it might take, of course, a long time, but did you think like, is there like a precise way to define what you say dynamical phase transition? If I have integrability breaking, is there like some partial? Is there a sharp definition?
Yes, that's an excellent question. And you can see that even for small systems, you don't see this very sharp behavior. I mean, even quantum fluctuations. I mean, not even, I mean, when you try to include quantum fluctuations, you see that the order parameters start to decay very quickly, sorry. I think in the experiments, what you do sometimes is that you look at very short times. Unfortunately, I mean, maybe this is cheating, but you can see that, I mean, if you look at very short times, you can still see some different behavior between something that decays very quickly to something that is going to asymptote to something that is going to, in principle, have these oscillations.
But then it could be like a sharp crossover, but transition is usually some singularity, right? And this might be missing. Right?
Yes, that's true. But sometimes what happens, for example, I mean, for these phases is a little bit more complicated, but what we did, for example, for Joseph experiment, is that we do time average sometimes, and the time average can help you to, it's not abrupt. I mean, I can show you, we have something that it's never a very sharp transition. There is, you can say, a crossover, but
it can be sort of like temperature for quantum phase transition. So you have like influence, something right of a phase transition.
Yes, so in a trap, the transition is never sharp. So when, I mean, not for the, I mean, in Joseph experiment, we try to see the sharpness of the transition, and it was not completely sharp, but we can see something that was stable, and at some point it decayed, and there was a crossover, but still you can define. Yes, it's not sharp. Yeah, we are not in the thermodynamic limit either. The experiment can only go to short times because there is dephasing. So you are right that it's not exactly a sharp behavior, but more like a crossover. But that's what happens for finite system in phase transitions too. So.
Great. So I think that's a good place to end. Let's thank Anna Maria again.